All right, Integrated Math 3 students. Today is going to be essentially our last lesson for radical equations. For the rest of the week, we're going to be just doing additional work just to really extend things with these radical equations, but everybody's been doing pretty well. I'll be adding the last parts of Deltamath today as well. So make sure that after you watch this lesson, you get on there and make sure you get that finished. That is due Friday the 20th. Yeah, Friday's the 20th. Let's go ahead and get right into it. Okay, so I need you to draw a line in your notes. And here are the directions for what I want. At the top, you're going to write radical equations graphs, because today we're talking about graphs of these radical equations that we've been solving for the past week. And so in your notes, you're going to write both equations, f of x equals square root x, and then you have f of x equals cube root x. All right, and here are your directions, because this video, I'm gonna have this video get paused. And so when it's paused, you are to graph using your calculator. So you're gonna see what this looks like on a calculator. Those that need to use Desmos on your laptop, you'll do that. Make sure you have a laptop to do that. Then you're going to draw a sketch of the graph. So in your notes, you can go ahead and, make an XY axis. Again, a sketch is very simple. It doesn't have to be detailed. I'm not even going to put numbers on mine, but go ahead and get that formed in your notes. And then number 3, you're going to list out as many characteristics as possible. Okay, so think about characteristics of graphs that we started the year identifying. That's what we're going to be doing. Okay, so any characteristic that you can think of, that's what we want you to do. Okay, so let's go ahead and let's get this paused and give you a moment to do this. So let's start with the graphing aspect of this. If you're using the Inspire or the 80 series, let me go ahead and pull all of these up while we're waiting. I'll let that load. But on the Inspire, all you have to do is hit Control X squared over here on the left side. Type in an X, hit enter, and you should get this graph here. License expired. Oops. Okay, never mind. I can't do it on the 80 series. Desmos here, we're going to hit the square root, and we have X. So there's Desmos, so that's what it would look like. Let's go ahead and graph the, I'm gonna go ahead and put x cubed in here for Desmos. You'd want functions, miss, and then we have this one right here, and we can put the 3 and inside x. So there's that one. Now we're gonna look at these one at a time, okay? We'll start talking about the square root function. And then on here, I'm gonna go ahead and put the cube root. So control, and then I'll hit the little caret button, 3, and then X. For those on the 80 series, you're using the math button, the cube root in it, okay? All right, so let's talk about these. Well, actually, we need to sketch them first. So hopefully your sketch is better than mine. For my cube root, it looks something like that, which is not very good at all, but that's okay. Let's talk about characteristics that could come up from this. So this should have been your mindset. What type of characteristics there are? Well, first off, x-intercept, right? That's a pretty simple one to talk about. X-intercept, and actually let me type these just because it's gonna be cleaner to read. We'll make that a larger font. There we go. Okay. X-intercept is going to be, we'll do an ordered pair. Well, look where it crosses the x-axis. That is 0, 0. Okay, for this, we call this a parent function, right? This is just the basic format of an x-intercept. Next, y-intercept. You'll notice that the y-intercept is exactly the same. Okay, y-intercept is exactly the same. What are some other things that we could talk about? Well, hopefully beyond that, perhaps you thought of end behavior, right? As x, and I'll write it this way, goes to infinity, y goes to, well, what's y doing? So x, here's positive infinity over here, right? as the x values go this direction, what's this green line doing? That's something to consider. Well, the y values are getting higher. They're going to also in positive infinity, right? What about as the x values go the other direction towards negative infinity? Obviously on your paper you can draw the infinity symbol. So what happens as this goes to negative infinity? Well, let's put negative infinity. Well, you'll notice that it doesn't really even go to negative infinity, right? But what do the y values approach? What's the lowest? What are the y values doing? Well, they stop right here at the origin. So we're going to say the y value goes to 0, right? That's all that's happening. It's never going to go past that if we're going that direction on the left there, right? All right, so in behavior is a whole characteristic. Think of something else. Let's see. Increasing, right? Increasing, decreasing. We talked about intervals of increase and decrease. So this is always increasing. You think about increasing, decreasing from left to right. So starting at the origin all the way to infinity, this graph is increasing. So we're going to write this in interval notation. From 0 to infinity, the graph is increasing the whole time. Is there a decreasing? No, it's never decreasing. So we're not going to put an interval of decrease on here. We have concavity. So that's talking about the right side of the graph, if you remember that from the chapter when we were graphing polynomials. Same thing applies here. How is this one, what's the behavior on the right side? That's what concavity is. Well, it's concave up, right? Concave up in this case, so that right side is going up. Okay. Other characteristics that we can figure from this. Positive. The graph, so this relates to if it's above or below the x-axis. Well, this graph is above the x-axis from 0 to infinity. Always, right? It's always going to be positive. Negative? No. I'm actually going to change this to no as well. Okay. A lot of characteristics here that we've learned and we're trying to reapply. Domain. Domain, remember, is the interval of all possible x values. So what is the domain? Is it all real numbers? That's what a lot of our domains were when we were learning about this. For polynomials, it's always all real numbers, but that actually isn't the case here. The domain, there are x values that don't exist for this graph, right? And think about it. It is a square root. What values can I not plug into square root? Well, that would be negative values, right? So we're going to put the domain is 0. I'm going to use a bracket here because that means 0 needs to be included in this. 0 to infinity is the infinity. If I can spell it, I've spelled it 4 times at this point. Okay, domain, infinity. Next, range. Range. Okay, what's the range? Well, that's all possible y values. Well, the lowest y value is 0, and the highest y value, well, that's positive infinity. This thing just keeps going up and up and up. So we're going to put 0 to infinity on this one. Okay, now domain and range is the biggest point of this graph. And actually in your Deltamath, that's what we're going to be focused on, are domain and range questions, okay? So hopefully through those you can get some good practice with domain and range. If you have any questions about them, let me know. I'll pull up some examples of that. But let's go ahead and look at cube root of x, and we're going to do the exact same thing. There's not really any other characteristics that I want to go into. Again, domain and range, those are the ones that I'm most concerned about. So I'm going to bold those. That's the ones that we want to make sure we understand, okay? Let's look at cube root. So on Desmos or in your graphing calculator, you have this function here, okay? So This is a different type of function. So let's go ahead and draw this. I'm gonna make this one blue. So we're gonna sketch this if you haven't already in your notes. Again, your sketch doesn't have to be beautiful. I'm using a mouse, so I don't have my Mobi still. I hate it, but that would be sort of what you want. I am going to just duplicate this, drag it over. Wait, oh, it's down here. There we go. And my camera's in the way. We'll go to the left side over here. All right, so we need to go through and edit all of this here. Okay. All right, we're ready. All right, hopefully you were able to get the idea of the characteristics for these graphs. We're gonna start with the x-intercept. So what is the x-intercept? Well, you'll notice on this graph, it is the origin, okay? And as a matter of fact, that means the y-intercept will also be the origin. So honestly, I should have just kept that there, but that's okay. So we're putting 0, 0. That's the x and the y-intercept for this cube root function. Now, what about the end behavior? As x goes to infinity, so we're looking on the right side of the graph, going to the right, we'll notice that the y values are actually going up, 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 up. So we have infinity again. This time we can actually go in the negative infinity direction. So as x goes to negative infinity, going to the left, what are these y values doing? Well, you'll notice the graph is going downward. It's gradually getting more and more negative. So that means it's gonna go to negative infinity. Again, you should be putting the infinity symbols here and not necessarily the words. Obviously the words are fine, but we usually use the symbol, so. All right, increasing. Intervals of increase. So last time, look on the green graph here, last time it was just always increasing from 0 to infinity. And we see that happening again here, right? Like it's going up from 0. But remember, we think about increasing from left to right. So starting all the way over here on the negative infinity, moving to the right, is this ever decreasing? Well, the answer is no. Look, it's going up, 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 and it goes all the way through the origin, up, 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 and it just never stops. So it's actually always increasing from negative infinity to positive infinity, always increasing. There we go. Is it ever decreasing? No, none. There are no intervals of decrease. This graph is always getting bigger as the x values increase. So that's what we're talking about. Okay, concavity. This one's still concave up because concavity is determined on the right side of the graph. Okay, in that first and fourth quadrant. If it's going down, it's concave down. If it's up, like ours here, it's concave up. What about positive? So this graph is always positive because it looks similar to the green one here. It's always positive after 0. Okay, every value greater than 0. So 0 to infinity. If I can spell it, there we go. 0 to infinity, it's positive. What about negative? Well, it's negative over here on this left side. Where's the beginning of that interval? Well, at negative infinity, it is it's a very large or a very small negative number. All the way up until 0, not including 0, that's going to be our domain on this one. Or excuse me, the negative interval where the graph is negative. Okay, domain and range. Again, I said this is the most important thing to note. So domain, what are all the possible x values? Well, actually all of them are allowable. It's all real numbers, right? But we're going to put it this way, negative infinity to positive infinity. I'm going to get real good at spelling infinity by the time this is done. Okay, negative infinity to positive infinity is the domain. So before we go on, a lot of you were maybe wondering, you know, here we couldn't solve questions. Remember, we get extraneous solutions from these equations that have square roots. But remember, we wrote down in our notes for cube roots and any odd power root, we don't have to check those solutions. Any solution that exists from a cube root or an odd root equation is not going to be extraneous. Here's why. The blue graph shows us why. All real numbers are possible. But in the green graph over here, we can only get and plug in these positive values, positive y values, okay? So this is a deeper explanation as to why that is. Now, again, I said you should always be checking your answers when you're solving these equations, but the cube root here, you don't have to. And if you can remember that rule, that's gonna be very helpful. Okay, very helpful. So what about the range? What is our range here? Well, we're going to get every possible y value that's negative from this left side. We're going to get every possible y value that's positive from this right side. So actually this one is exactly the same. Negative infinity to infinity. All right, and so this is the main point of this, is just to talk about domain and range. Let's go ahead and pull up Deltamath. All right, so I've pulled up Deltamath here. I'll zoom in just a little bit. Here are the domain and range questions that you'll be dealing with. These are ones that I have made. Oops. Here's the problem right here. So here it wants you to find the domain and range of the function. And you'll notice that I've given a different type of function. It's not starting at the origin. So your domain, you're gonna have to figure that out based on where the x values start, okay? And so in the range, same thing. Where do the y values, what's the lowest y value, what's the highest y value? And we have different questions that you'll see throughout this. Some of them look a little bit strange. Like look at this one. We haven't seen one that does that. So you're just gonna have to think through your domain and range knowledge of what that is, and take your time, make sure you get the right answer. Now, I only put 4 attempts on this. If that's not enough for you to do, then you need to let me know so that I can increase that for you. But I wanted to make sure this wasn't like the other ones where you're solving and you get lots and lots of attempts, because you could just exhaust the list of options here just by clicking. But there's a lot of options, so and a lot of combinations, 25 combinations. I think that you shouldn't be able to just guess this. There's 25 possible combinations. So a lot of examples here for you to do. There's a cube root there that you see. So that's gonna be the practice that you're gonna need to do. Okay, so we're 18 minutes in. Go ahead and draw another line in your notes. So we've got our graphing down. So now what we're interested in is solving radical equations graphically. This is the final skill for this unit. We are taking our test. Our test will be 23rd and 24th. Distance learners will be the 24th, but depending on A day, B day, for those face-to-face learners, 23rd, 24th is when we're taking our tests. So this is the final skill. And it's actually something that you guys already have seen before. This is going to be the type of question that we'll be looking at. We want to satisfy, it's this idea of f of x equals g of x. We're going to graph both functions, and really what we're looking for is intersection points, okay? So let me get us a problem to do here. We're going to go ahead and start with identifying f of x. And we're going to identify g of x. So go ahead and set up your notes like this, except I don't want f, I want g. Okay, let me get us a problem here. All right, so we've got us a problem here. So we have f of x equals the square root of 11 minus n, and g of x is 3n minus 1. So what are the solutions that satisfies f of x equals g of x? Now, typically what we would do, and I'm going to undo this, so don't change your notes in any way. But really what we would do, this is what this question would normally look like right here, is we'd set them equal to each other, and you have the skills to solve them now. Square both sides, get n by itself, check your solution to make sure it works. But we're changing that up now. And I know that one of my face-to-face learners, Jace, I'm gonna go ahead and call him out, has been doing this pretty much the entire chapter already. And I haven't gotten onto him because this is actually one of our essential standards, is this f of x equals g of x. So what I want everybody to do is go ahead and graph these. Okay, so on my calculator, we're gonna type in the equation, negative, we want 11 minus, oh, come on now, 11 minus x. We're not gonna type in n. Okay, so there's 11 minus x. And then hit tab. We want to graph the other equation, which is 3n minus 1. So square root 3n minus 1. Yeah, exactly. We can't put n in. We have to put x. Come on now. There we go. All right, so what we're looking for, what we're going to write here, or I'm going to type it, the intersection of the graphs, the x value of the intersections of the graphs are the solutions. Okay, so what we want, and go ahead and write this down. This is like the important note here that you need. I think we all kind of knew this already, because again, this is kind of a review topic. We've already seen ways to solve these before, but if you're using the 80 series, what is it you have to press? You have to press second calc. It's at the top, and you do intersection for Inspire users, analyze graph, intersection, left to right. The x value is our solution. Let's see this on Desmos, which again is not allowable on a test. So I want 11 minus x. Let's graph another one here. What was the second one? 3x minus 1. So let's pull that up. 3x minus 1. We can just click there. Okay, the solution is 3. So where they intersect is where our answer is. So we're going to say x equals 3, and we are done. We got it correct. Do we need to check the solution? No, we don't need to check the solution at all. All right, so let me show you what I mean by this is exactly what we've been doing, and all we're doing is changing up the format. So here is like an original equation that you guys would have solved in the beginning of this unit. So all I'm going to do is take the left side of it, x minus 8, subtract x. So this is the entire left side of the graph, and then on the right side we have negative 8. And that's all I need. So we're going to go ahead and graph these. I'm going to use Desmos just to make this a little bit cleaner. So we have x minus 8, and then minus x is down here. Let me make sure that what is the answer on this one? Oh yeah, this one's fine. So then the other, we just need to graph y equals negative 8. That's all we're doing. So you're just gonna go to the graphing aspect of this, and we're gonna do y equals negative 8. So there we go. We zoom in and we see that there's 2 points of intersection, 8 and 9. Those are our solutions. Okay, that it's that quick and that easy. X equals negative 8 and 8 and 9, not negative. 8 and 9. So that's going to be our solutions to this. And if we solved it, we'd have to do a quadratic and all of that stuff, okay? Let's look at some that have maybe no or one solution to them. Okay, so let me reset this. Again, you need to write these as I write them. All right, so we've got this new setup here. Go ahead and write out this equation. Again, there's quite a bit of steps on this one, but we could have 2 solutions on this one just because we're gonna end up with a quadratic. But let's go ahead and graph this. So I want negative 2 plus, I think it was negative 2. Let's go back, let's see. Negative 2x, and then plus 31. So that's that graph. Let's go back home here. So there's what that graph looks like. And we're gonna change this to just X, right? That's gonna be it. And you'll notice that this graph crosses one time, okay, at 3, which actually should be the answer to this. So that's all we're doing, equals 3. There we go. So now let's look at one that has no solution. For instance, we know that this one here I'm about to write is impossible, because this was the first example we ever tried to solve. -2 and square root x, right? So let's talk about why. Let's look at that. So square root of x, -2. Remember, this one had no solution. Well, we got 81, right? Or no. It was -9, wasn't it? I think that was it. -9. Square root of x equals -9. That was the first example we did. And we got no solution. We got an 81 as x, but then when we plugged it back in, it turned out to be extraneous. So let's go ahead and look at that. Square root x, there's our graph, and then we want y to equal -9. Well, you can see there's no crossing here. Oh, here's the line down here, right? They're never gonna touch. Let me actually make this a letter. Can I just make a slider, please? Let's just do S. Okay. Okay. So as any of these positive values, so this is sort of the idea that we want to get at here. If I'm making S, this purple line, positive, there's always going to be a solution. But as soon as I go 0, even there's a solution. But as soon as I go negative, it becomes extraneous. There are no solutions. So that's really the idea here. As long as these are touching one another, there are solutions. So let me find an example that has no solution that looks kind of complicated. Okay, so I guarantee that this example will have no solution to it. So let's go ahead and look at it. Let's graph both of these. Also, solving this would probably not be very fun. No, this would not be fun to actually do algebraically as well. So let's go ahead and graph this. We want 1 minus 4 minus 2x. So there's our first one, that red one. And then let's go ahead and we'll graph on this row here. We have 3x plus 1 actually is the formula. Okay, look at that. So these graphs never touch. They actually look pretty cool, right? Sort of opposite swirling pattern here, but they're never going to touch. Now, if this had been a +2, still wouldn't have. So that didn't even end up mattering. But if we added 1, that actually made the difference right there. So that would have a solution, and it would be a decimal, so not a whole number like we've been getting. But there's a lot of ways that this is caused. Okay, so that's what we're looking for. One more example that I want to talk about is if I did, let's do x here. And another example is, let's get rid of this. -1 minus 2x. So here's another example. These two equal to each other. They're just not crossing. So those are why you would have extraneous solutions. It's when these graphs don't cross, and a lot of that's caused by the properties of radicals. As soon as I graph a cube root, by the way, look at this cube root, 3 solutions to it. Cube roots will always have solutions. No matter what I put here, let's change this back to S. No matter what I put, these graphs will intersect anywhere, right? Look at the purple line and how it always crosses. You'll always find a solution to these graphs at some point, even a flat line. There is no situation where a cube root will not have a solution. Okay, so that's that idea of why do we not have to check the cube roots ever? This is why. Okay, there are no extraneous solutions. So hopefully that makes sense. let's look at some Deltamath. I've got more work to do with Deltamath as far as putting problems up, but let me give you just an example of what you're going to be looking at. So far this is what I have on here. I've only got one question. I'm probably going to end up with like 7 or so, but I gave you 5 attempts on it. Let's look at this problem. So you're going to see it says the functions are given f of x equals g of x equals, and I've labeled clearly the colors that they are, red and black. Their graph below. What are the solutions that satisfy f of x equals g of x? So you just want the x value or values that make this true, okay? And on this one, I might tweak this a little bit, but here there's only one. So right here, that intersection, you would put in wherever that x value of that intersection, it looks like it's 10. So I've kind of already answered this one for you, but that's going to be the idea for these. Anyway, that is our final lesson for this unit. We're going to be doing some other stuff to close out the week, but we'll go ahead and stop this here.